Hello everyone, my name is Xincheng, and I'm presenting our paper SurfShare Lightweight Spatially Consistent Physical Surface and Virtual Replica Sharing with Head-Mounted Mixed Reality. This project is situated in the field of symmetric remote mixed reality collaboration, which allows users to collaborate with both physical and virtual content. Such a collaborative paradigm retains physicality in the real world to allow users to collaborate with familiar social and spatial protocols. Our work takes inspiration from projector-based physical surface sharing. SurfShare contributes lightweight physical surface sharing with head-mounted mixed reality. We additionally overlaid a virtual workspace with ad hoc creation of virtual replicas. We studied the impact of our system on collaborative experience, and in particular, prosemics. To start, here are the main features of SurfShare. First, our system situates two remote users in a spatially aligned workspace. Secondly, our system provides a shared physical surface for users to collaborate on physical tasks. And finally, we overlaid a virtual workspace on the shared surface, allowing users to ad hocly create virtual replicas from 2D shapes. Our system only requires a pair of Microsoft HoloLens 2. Now let's go over the requirements, challenges, and solutions in designing and implementing the system. First, a symmetric remote collaborative system needs to spatially align two remote environments. A key challenge here is to enable low-friction setup of a common reference space. To do so, we use the virtual portals as spatial anchors. So here, user 1 on the left starts with defining a virtual portal on their desk. A copy of this portal shows up on user 2's desk on the right. User 2 then places the portal, which then anchors the user 1's position in user 2's environment. User 2 then defines their own portal, which then shows up in user 1's view. The spatial alignment is now achieved by checking the transformation matrix between the two portals. With the spatial alignment configured, our system implements merged physical surface sharing. The virtual portals now streams video of remote users' view of their respective physical surface. A key challenge here is to only bring relevant physical content into the collaboration. For example, here, only the user's hands and checkers shows up, while the desk color and texture are removed. To achieve this, we implemented background subtraction with HSV thresholding. Although more advanced background segmentation exists, we found a thresholding technique best balanced the performance with the limited computational resource on an AR headset. An important feature of our system is lightweightness. Unlike prior projector-based surface sharing, our system only uses the headset sensing capability. However, the continuous version of a head-mounted camera requires video stabilization, which requires real-time plane reprojection. Our system reprojects the remote user's video to the portal using the real-time camera intrinsic and extrinsic. Here we show a comparison between such a real-time reprojection and naively stretching the video to fit. As we can see at the bottom left, when naively stretching the video to fit the portal, the video distorts as the user moves their camera. In comparison, the video is free of distortion and stabilized with real-time reprojection. The lightweightness of our system brings flexibility of configuration. The key challenge here is to satisfy various collaborative and spatial dynamics. Our system does support movable virtual portals. As we can see here, the portals can be merged into a shared surface, laid side by side as separated workspaces, and configured with different orientations according to physical layouts. The final key feature of our system is virtual workspace. The key challenge here is to overlay a virtual workspace and coherently integrate it with the physical surface. We propose bridging the physical and virtual workspace with virtual replicas. Here is how it looks like. A user can cut colored papers into shapes and create the corresponding virtual replicas. These virtual replicas can be customized with extrusion, scaling, and scale, making them suitable for prototyping purposes. Now let's go through some application scenarios. First, using shared surfaces, users can engage in shared activities on the physical picture. The second application scenario is remote demonstration. Here on the right side, A remote instructor is using virtual replicas of a tangram puzzle to construct a shape, while the local user on the left side can follow along with the physical objects. The third application scenario is shared mixed reality recreational activities. SurfShare makes remote mixed reality physical games possible by creating virtual objects with physics that can collide and interact with each other, as well as the physical environments. Here, two users are playing a mini bowling game on a desk. The last potential application is collaborative virtual content authoring. Here, with ad hoc creation of virtual replicas, two users are collaboratively building a castle. The first part of our evaluation involves 10 participants experiencing with the 4 example applications and filling out the standardized system usability scale. From the results, we found the system to have a good usability. Then we did a more comprehensive study with a design and prototyping task. We situated 6 dyads of users. Each dyad is situated in the corners of a large lab. The corners have different spatial layouts to encourage them to use physical resources differently. The study continues in 2 phases. First, the participants brainstorm and design what to prototype on shared physical surfaces. They then prototype by creating virtual replicas from colored papers or drawings. We gathered qualitative feedback revolving around 2 research questions. First, how does lightweightness and flexibility impact remote collaborative experience? Second, how does ad hoc 2D virtual replicas enhance remote collaboration and lo-fi prototyping? For the first research question, we found the portal layouts imply a collaborative dynamics. We found that overlapping portals are more suitable for closer collaboration, while separated portals encourages labor division. Additionally, the lightweightness and flexibility of our system allows portal reconfiguration to adapt to physical resources in the space. For example, some participants set up the portal vertically on a whiteboard in the design space and then reconfigured to the desk in the prototyping phase. We also found the configuration of the portal defined the spatial scale of collaboration. Some participants further separated them to allow for more space during the prototyping phase. Now, for the second research question, we found that ad hoc virtual replica creation is intuitive and efficient. Here are some results from our participants. We actually found that participants with some prior 3D modeling experience can use our system to go beyond low-fidelity prototyping. For example, here a pair of participants create a cotton car in the third picture here, which is my favorite of those. This brings us to the end of this presentation. Thanks.